All right. I know I am early for a Tech Tuesday discussion, so I apologize, but I have a scheduling conflict, and I wanted to get a discussion going, and I didn't want to miss Tuesday, so I'm a half hour early. Laura, thanks for joining in, and I appreciate you jumping online with me. I'm a half hour early, so I have a conflict at 12:30 Eastern with another meeting, and well, the show must go on, right, Laura? Laurel? Almost called you Laura. My cousin's name is Laura. All right, I'm going to mute my phone, and we are going to get ready for... We're going to get ready for another IAEI News Live. And this session, I want to talk about continuous versus non-continuous loads. And that's the topic of today for IAEI News Live, continuous and non-continuous loads. And it all starts now. All right, so, okay, we got Laurel, we got research. Research is online and ready to go. I have my copy of NFPA link opened. And so over the last few weeks, we have really dug in deep on ampacity, determining the right conductor size, determining the right overcurrent protective device. We've talked about conditions of use. We went through Article 210 and 215. We even did some examples. But this session, I wanted to talk about something that I think we take for granted, in my opinion. If you look at what we did over the last few sessions here on IAEI News Live, we calculated the necessary ampacity for a conductor and the overcurrent device. And we said we need to understand what are the continuous loads and what are the non-continuous loads. Eli, thanks for joining in, buddy, for a little bit early, 30-minute early. IAEI News Live, and the topic today is continuous and non-continuous loads. So we went in 210 and in 215 and also in 310, and we talked about continuous and non-continuous loads. We understand the 1.25 factor, and that goes back to the reason we do 1.25 times a continuous load is because our electrical distribution equipment, circuit breakers, fuses, panel boards, I would say even some transformers, others, are 80% rated. Now some of them, some equipment can be purchased 100% rated, but it all begins with a calculation that assumes that you know what is a continuous load. It doesn't define what a non-continuous load, because if it's not continuous, then it's non-continuous. Hey, good morning, Nihad. All right, so let's take a look at what the definition of continuous load is, because I think you might be surprised at something here. Whoa. Okay. I have my copy of NFPA link open, and hopefully you have your NFPA link, or you have a code book. I'm looking at the 2023 edition. And here's what it says. Here's what NFPA link says, or the NFPA document. I'm using, again, NFPA link. Love the program. It says a load where the maximum current is expected to continue for 3 hours or more. Now, in many cases, we shorten that up. We'll say if the load continues for 3 hours or more. So I could say, does my HVAC system stay on for 3 hours or more? Do I have a load that will persist for 3 hours or more? And we use this continuous load term pretty generically because we always, at least I have, and I know I've heard others do this, leave out the word maximum. Now, why is that important? And you might go, yeah, Tom, why is that important? Well, did you, in your Laurel and Eli and Nihad, if I have a motor that runs all day, is that a continuous load? We were doing transformer training, and they said, well, a transformer is a continuous load. And then my comment was, well, it depends on what the load current is on the load side, right? If that load on the load side of a transformer is a continuous current. And then I got into a discussion where an individual said, well, no, a transformer itself is a continuous load, just like a motor is a continuous load if it runs for 3 hours or more. And a transformer will deliver power for 3 hours or more. It delivers power all day. But the word maximum is problematic. So if you think about a motor, the current range on a motor, you have inrush currents and you have full load amps. If you would ask me, what's the maximum current that a motor has? I can't tell you it's the full load amps because I know that the locked rotor amps is going to be more than the full load amps. So a motor can never be, just as a motor itself, the motor cannot be a continuous load because the inrush current does not last for 3 hours or more. That's the maximum current that is expected. It says a load where the maximum current is expected to continue for 3 hours or more. Where the maximum current is expected. The maximum current on a motor is not full load amps, it's the inrush. And I wouldn't expect inrush current to last for 3 hours or more. Lighting is a good example of a continuous load. You turn lights on. If I have a circuit and I know my lights in a warehouse are going to be on all day, that's a continuous load. I think that's the low-hanging fruit of a continuous load. Laurel brings up, now, Laurel's going to 430. So in the National Electrical Code, we'll tell you in some cases this load is to be considered continuous. Then it takes the question out of it. So if I say continuous, I'm using NFPA link now, continuous load, and I'm going to search, there's the definition. I'm going to search all of NFPA 70. You've got 427, fixed electric heating equipment for pipelines and vessels shall be considered continuous load. Fixed outdoor electric de-icing and snow melting equipment shall be considered a continuous load. And the reason that's important, again, because of everything we did over the last few weeks, we used continuous plus non-continuous. And if we don't understand what a continuous load is, it's problematic because now I'm sizing my conductors wrong, I'm picking the wrong overcurrent devices, and it's a snowball effect. So if you look in 210, it tells you how you're determining the size of the minimum size of the branch circuit. In 210, it'll also tell you that the overcurrent device cannot be less than 125% of the continuous. And that's, again, 125% is 1 over 80%. 1 over 0.8 equals 1.25. So when I multiply a load current by 1.25, I am inflating the load current so that when I pick my overcurrent device, that current is going to be 80% of the rating. Okay? So for example, a 100 amp load. If I take 100 amps times 1.25, I get 125 amps. If I take a 125 amp breaker, which would be adequate, but I'm only have 100 amps, I take 80% of 125, and that's 100 amps. So by inflating the load current by 125%, and selecting my overcurrent device, I've already incorporated the 80% derating factor for the overcurrent device. Make sense? So it's really critical that we understand that. And we'll use the term continuous load, and anytime you have and see that term continuous load in the National Electrical Code, that means we're going to apply a 1.25 factor to it. That means, and that's critical for what I'm, not for the conductor. It has nothing to do with the conductor. It has everything to do with the equipment. The only reason I will multiply my load currents by 125% is when I'm selecting my equipment that's 80%. If I, and you'll see there's some exceptions. If my equipment is 100% rated, then I don't do the 1.25 times the continuous because I can handle the current in the equipment. So, for the most part, in all of these applications, in a lot of these applications, it will use the term continuous load. We saw it in 427 for electric heating equipment for pipelines. We see it in 426 for snow melting equipment. In 424, did I do 424 already? Yeah, no, 424. What's 424? Fixed electric space heating equipment. That's considered a continuous duty. Continuous duty. 210.19a, where that's 210. Considered to be continuous loads. So 625. Article 625 for electric vehicles, section 625.42 tells us that electric vehicle charging loads shall be considered to be continuous loads. So I don't have to incorporate, I don't have to tell you, take the load of the electric vehicle and multiply it by 125%. I don't have to do that. By stating it's a continuous load, anywhere else, like in Article 210 and 215, when I'm determining the minimum size branch circuit or feeder, etc., I'm going to say take 125% times the continuous loads plus the non-continuous. So the fact that back in chapters 6 and 5 and 4, etc., when I say it's a continuous load, then I know to do the 125%. Now, Laurel keeps bringing up Article 430, and we're going to get there, and she's latching on to the fact that in the motor articles, based upon our earlier discussion, a motor cannot be considered a continuous load because of that maximum value. So back in Article 430, we take care of the continuous load directly by using a 125% factor. Some cases it's 115%. But we take care of the ramifications of a continuous load on equipment in 430 by using that 125% number. And we're going to take a look at that. But that's a very important piece of this discussion, is to understand that a continuous load is handled in the National Electrical Code. We'll identify what's a continuous load. In some cases, you may be presented with an application where the load that you're looking at, you know, is a continuous load just because of the way it's being applied. Or you know it's not going to be a continuous load, and then you'll address it based upon the application. But in some cases in the code, we'll tell you what loads are considered continuous. Electric vehicle charging equipment is one of those applications. So I'm just looking through the different areas to see shall be considered. Let me see if it's considered. I'm going to search on considered continuous load. There's your 427, your 426, your Article 6 branch circuits that supply signs. Here's another one. So 600.5 branch circuits that supply signs shall be rated in accordance with 600.5 C1 or C2 and shall be considered to be continuous loads for the purposes of calculations. So that's, again, it's a critical piece of the pie. Now I don't know how to, hold on, I don't know how to get out of this. There we go. Oh, wrong one. All right, so that's cheese, isn't it? So I think, go back to search. Why don't I have search? Let me just do a refresh, reload on my NFPA link. I think I zoomed way too far out. Okay, there we go. Now we're cooking with gas. All right, so now let's go to Article 430 because Laurel is over there in 430 and she's been patiently waiting because I wanted to make sure that I covered a few of those others where we specifically call out continuous loads. We're not going to call out non-continuous loads just because, again, you call out a continuous load and you're done and you're kaput. Now, I think that also you've got to be careful in the code, and there might be examples of where we double dip in the continuous world. You don't want to have a code section mandate 125%, but call it 125%, not realizing, not where the user of the code doesn't necessarily realize what is that 125% there for. Is it there for the continuous load or is it there for some other reason? It just says 125%. And if you don't assume that to be the continuous load, and then you say, well, it's a continuous load, I've got to do the 125% based upon the rule, and then I have to add another 125% because the continuous load, now you're double dipping. And what does that do? That doesn't create a safety issue per se, and the reason I say per se is related to what level of protection does the overcurrent protective device provide for the equipment. Because if I double dip on the 125%, it could drive my conductors to be larger it'll also drive the overcurrent protective device to be larger. That may not be a good thing. You'll have more capacity on the circuit, but because the overcurrent device is inflated in size, you may have less protection. Now, I'm outside of HVAC equipment. I cannot say that many other equipment will specify the size of the overcurrent protective device. You know as well as I do that in the HVAC world, it'll tell you the minimum circuit ampacity and the maximum overcurrent protective device. And those typically align based upon, say, a 60 C ampacity value and align with the UL standards on proper conductor sizes for those overcurrent protected devices. But they give you the minimum and the maximum overcurrent protected device, and if you need to increase the conductor because of conditions of use, you're fine. It's not going to be an issue. But they'll give you the two barriers, right? The two lanes. You got the white solid line on the right, and you got the yellow solid line on the left. One of those is the minimum circuit ampacity, and the other is the maximum overcurrent protective device, where you need to be in the lane or what size vehicle you bring down that lane. We don't really care. You're going to bring the size of the vehicle that you need to carry the payload, but we just need you to stay within those two guardrails. Now in 430, you'll notice now, Laurel, okay, I'm going back. Eli, we're going to address the VFDs as well. Bum, 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 bum. So Neod says, like I did, if that motor's running all day, I'd say it's a continuous load. Now, 430.22. Let's go to 430.22. I like this. See, this is why I like having research around. Laurel, you are the girl. 430.22 tells us, look at this, conductors that supply a single motor, conductors that supply a single motor used in a continuous duty application shall have an ampacity of not less than 125% of the full load current rating. Now, they take the route of 125% here, and this is where we could run into some challenges in double dipping, right? So Nihad's statement that I would consider this motor, if this was a motor that was running all day, I would say it's a continuous load. If I didn't understand that word maximum, which quite frankly, I didn't for a while. It was John McCamish that made the statement one day. He was looking at a task group, chairing a task group. And he brought he made the comment that, well, motors cannot be a continuous load. And I was like, wait a second. If that motor runs all day, how can it not be a continuous motor? Just like Nihad went down and said. And he looked at me and goes, well, you got to read the definition, Tom. And then we opened up the definition together, and I looked at the defined term of continuous load, and I saw the word maximum, and he goes, what's the maximum current on a motor? And I'm like, oh, man, good freaking point. Very good point. So Article 430 has to address continuous load itself. And they do it with the percentage. Now, there's a plus and a minus to that. I didn't have an issue with it until I realized, well, these are two different things. Or there are two different ways of saying the same thing. everywhere in the code, when I want something to be multiplied by 125% for determining the size of the branch circuit and the conductors, etc., I'll say it's a continuous load. Except for here, I say 125%. And that, if you are in the world of using continuous load all the time and it's a defined term and it's not used here, I can completely understand somebody making the mistake of doing 125% and then also doing another 125% for the continuous load. Now, you may say here that, well, Chapter 4, now remember, chapters 1 through 4 apply generally. Let's take a look at that. Let me do this. Let me open NFPA link again. I was in NFPA 70E. That's another nice thing about NFPA link is you can open multiple instances. 90.3 tells us that chapters 1 through 4 applies generally to all electrical installations. And then chapters 5, 6, and 7 supplements or modifies chapters 1 through 7. Now, what I don't have in this is text that says chapters 1 through 4 can supplement or modify chapters 1 through 4. Okay? So I could make the argument that here, where we say for a single motor, conductors that supply single motors used in continuous duty application shall have an ampacity not less than 125% of the motor full load current rating. And say, well, that's not going to modify, if this is a branch circuit feeding this motor, that's not going to modify in 210. So I'm still going to do my 210, and I'm going to say that this motor is not a continuous load. And I'm going to do my two calculations, my one calculation based upon conditions of use, my second calculation based upon continuous load, and I'm not going to do 125% times this motor load because it's not a continuous load. And then I'm going to do all of that evaluation, and then I'm going to come back over here and say, oh, well, this is a motor load. So now my conductors, my conductors that supply a single motor used in a continuous duty application has to have an ampacity not less than 125% of the motor full load current rating. When I would already get that done if I just called this a continuous load and did it all in 210. So does Chapter 4 modify 210? Do they complement each other? Or is it something totally different? Just when you thought the code was simple, right, Nihad? Since the inrush current is transient in nature, I don't think it should be considered maximum current. I agree. It's not. That's why a motor load is not considered a continuous load, and that's why you need this language. But now, so, Nihad, and everybody else on the phone, if we changed this, if we simply said, single motors shall be considered a continuous load based on the motor full load current rating as determined by 430.6A1. But look at this. Look, boy, there's more to this story. Look at this. Boy, so you have this is why motor loads can be a little bit more complicated. It's easier said than done to say, well, treat this motor as a continuous load and handle everything in 210. This tells us the minimum size of the conductor. 125% of the motor full load current rating as determined by 430.6A1 or not less than specified in 430.22a through G. So 430.6a1, 430.6a1. What is another cool thing about NFPA link? You see that? That's a hot link. I click on it and boom, it pulls that up. And then you just gotta do that. Other than for motors built in low speeds, ampacity conductors shall be used instead of the actual current rating on the motor. So what they do, so here's what they're doing. Oh yeah, this is another very important thing. Another very important thing to remember about motors. They size the equipment based upon these generic values and not the marking on the motor itself. Because if you replace that motor with another, the details specific to each of the motors may change, and you're not going to change the infrastructure, okay? So they want to make sure that you have a conductor sized and appropriate for a circuit for that specific motor, for that type of motor, or that, let's take a look at the tables. 430.247. This will tell you based upon horsepower. This will tell you based upon horsepower and the voltage what the full load currents are for those motors. So we do a lot of the calculations based upon tables and not the motor itself, because the table is going to give you a number that will be greater than the full load amps of the motor that's going in its place, so that you have an infrastructure that can accommodate the replacement of the motor. So they want you to do certain load-related determinations based upon these values and not the actual motor. Nihad says, and I did miss it, I think you missed it, since the inrush current is transient in nature. Yes, that's right. That is correct. Yep, I think I picked that up. 90.3, yes, needs some work. So chapters 1 through 4. You know what, Dawn, I'm seeing what you're saying. I'm buying what you're selling there, and I think that the restructuring of the NEC should address it. But this is a really good example of how, if I have a branch circuit that's feeding a motor, I'm going to go to 430, because it's a much more complicated than just saying it's a continuous load. .430 has some intricacies, and honestly, that's equipment for general use. If we said 1 through 3 applied generally, and chapters 4 through 7 can supplement or modify 1 through 7, then maybe that would be more accurate, because this is equipment that I'm going to size the branch circuit or feeder a little differently. I'm going to use values based upon these tables. But honestly, Dawn, I think that if you just said a single motor that is continuous duty is a continuous load based upon the full load currents as determined in Article 430, period. The moment you say it's a continuous load, you're going to do 125%. Now let's go back. Let's go back. Hold on. I didn't finish 430.22. Single motor. Because remember, there's A through G. So we did 430.6A1, and that is the tables, okay? Those are the tables. In 430.6A1, we have the tables. It says, or not less than it's specified in 430.22A through G. Now, A is direct current motor rectifier supplied. So these, and then you have a multi-speed motor, you have a Y-start delta running motor, you have a part winding motor, you have other than continuous duty. So obviously it's not a continuous load, so you're not going to do the 125% there, and that's not in that section. Separate terminal enclosures, okay. Conductors for small motors. So it is a little bit more complicated, but I think the 125% could send people down the wrong road. Keep in mind that 125% is there for the 80% based upon the equipment. That is there for the equipment that's supplying power to this motor, not for any other reason. Now, in direct current motor rectifier supplied, for DC motors operating from a rectified power supply, the conductor ampacity on the input of the rectifier shall not be less than 125% of the rated input current to the rectifier. So that would be a continuous load, and they're taking the rectifier not on the secondary side. It says for DC motors operating from a rectified single-phase power supply, the conductors between the field wiring output terminals of the rectifier and the motor shall have an ampacity not less than the following percentages of the motor full load current rating. They do 190% and they for a single phase half wave and 150% for a full wave type. Now, again, those are a little different. My device is locked. My phone is locked. All right, new markdowns taken. We can shop more. All right, I love these texts. So in any case, you still have the 125% for continuous now, but they don't say it's continuous. It is continuous. Don't double dip is my message, right? Now, somebody brought up, Steve, there's Eli. Was it Eli? Yeah, Eli brought up this. Depends on the duty cycle of if VFD is involved. That's right. So now we have the other aspect that you have something in between the branch circuit overcurrent device and the motor. You've got, say, a drive. Now, what we just saw here was a Y-start delta run motor. So in this case, well, no, I didn't have that. I had a direct current rectifier. In this case, that was, and this is continuous duty application motors. In this case, the current for a direct current motor rectifier was still 125% of the input current for the rectifier. Multi-speed motors, they say for a multi-speed motor, the selection of branch circuit conductors on the line side of the controller shall be based on the highest of the full load current ratings shown on the motor nameplate. The ampacity of the branch circuit conductors between the controller and the motor shall not be less than 125%. And then the Y-start delta run, for a Y-start delta run connected motor, the ampacity of the branch circuit conductors on the line side of the controller shall not be less than 125% of the motor full load current, as determined by 430.6A1, and that's those tables. And the ampacity of the conductors between the controller and the motor can't be less than 72%. Then you have a part winding. Okay, so, and then you have the other than continuous duty. So I'm having a hard time with E because it says, well, 430.22 is single motors. Streaming Independent Alliance, Facebook. Continue. I want to continue. We just lost our Facebook feed, and I'm not sure why, but we did. All right. I turned my phone. I just put my watch. My watch was dead. I put it on, and now it's like I'm getting texts from all weekend because I didn't have it on. Anyway. So The parent text of 430.22 says conductors to supply a single motor used in a continuous duty application. And then in E, it says other than continuous duty. I guess they wrote it as a positive text instead of an exception. All right, then you have small motors. So now, was it Eli mentioned the VFD? Somebody else mentioned. Got Steve, good to see you, buddy. Don Gannier, Willie Snyder, Michael Hofkin in the house. And then you got Don Gannier says, I'm thinking of the ampacity adjustment rules in 310 that modified by the rules in 376. Yeah, that's a good point too. And what Don was speaking to was our discussion about this. Chapters 1 through 4 apply generally, and then 5, 6, and 7 can modify 1 through 7. But Dawn's pointing out the fact that in Chapter 3 alone, you've got modifications from one article in Chapter 3 to another article in Chapter 3. So that's just ungood. All right, so now let's look at 430.32. 430.32 is titled Continuous Duty Motors. More than 1 horsepower. Each motor used in a continuous duty application and rated more than 1 horsepower has to be protected against overload by one of the means. So now you're getting into overload protection. So in the first 430.22, we talked about selecting the circuit conductors. We did that based upon the 80% when it's a continuous load. But they call it continuous duty, and they built in the 125% in Article 430. Your challenge is when you're doing, if it's a branch circuit, if you're doing your calculations in what do you call 210, right? 210.20, I think it is. All right, so now when you get to 430.32, you've selected your conductor. You know it's 125%, so the ampacity has to be at least that. And ampacity is conditions of use. So depending upon the temperature of the environment, the number of conductors that you have in a raceway, that's going to tell you the size of the conductor, which the size might be large, but the ampacity is still lower because of the conditions of use. So there's a difference between the size of the conductor and the ampacity of the conductor. The size might still be large, but the conditions of use will drive the ampacity down because of the multiplying factors. All of that still applies. Now in 430.32, we are picking the overload protection for the motor. Remember, Article 430 applies to the motor. 240 still applies. I still have to protect the conductor from overcurrents, short circuit, and overloads. But 430.32 says each motor used in a continuous duty application and rated more than 1 horsepower has to be protected against overload by one of the following means. You either have a separate overload device, you have a thermal protector or electronically protected, or you have an integral protection with the motor. And then if you have a motor larger than 1,500 horsepower, you have embedded temperature detectors, etc. that will. So for very large motors, we have RTDs, which are basically devices that measure the temperature in the windings, either the rotor and the stator, or both, and then they will adjust the protection for that motor because of heat. All right, so that's the overload protection for the motor. Then you have 1 horsepower or less automatically started. Any motor of 1 horsepower or less that is started automatically has to be protected against overload by one of the following: either a separate overload device, thermal protector, or electronically protected, integral with the motor, or impedance protected. Again, we're talking about protection of the motor from overload. And then C in 430.32 says where the sensing element or setting or size of the overload device selected in accordance with 32A1 or 32B1, that again is the small motor versus large motor, where that sensing element is not sufficient to start the motor or to carry the load, then you have the ability to go to an increased size. Because it says higher size setting elements or incremental settings or sizing shall be permitted to be used provided the trip current of the overload device doesn't exceed the following percentage of the motor nameplate full load current. And you have motors that are marked with a 1.15 service factor, 140%. Motors with a marked temperature rise of 40 degrees C or less is 140%. And then all other motors are 130%. You've got to let the motor start, basically. And then in D, you have 1 horsepower or less, and you have to provide your overload protection as above for the small motors in B, Bob. And then you have some rules for when it's not permanently installed. And then you have wound rotor secondary. So Part 2 of Article 430 talks about the circuit conductors. Part 3 talks about the motor. And now, what I don't like about the title of Part 3, it says motor and branch circuit overload protection. But everything in here says motor protection. I would have to say you can't. Dawn, I'd love your opinion on this. I'd love anybody's opinion on this. I can't say that Article 240 doesn't apply, which tells me I have to protect a conductor at its ampacity. Based upon what I'm reading here in 430.22 for single motors, 430.32 for continuous duty motors, nothing in here tells me that I do not have to protect that branch circuit conductor at its ampacity based upon the requirements of Article 240 and also the conditions of use in 310. Right? So, for example, my overcurrent protection for the conductors that are supplying this single motor that is continuous duty has an ampacity value. I have to protect that conductor at its ampacity. I can go to the next larger size, but I still have to protect the conductor at its ampacity. Now, the overload protection for the motor may be less than the full load amps, or the motor overload protection could be less than the branch circuit overcurrent protective device that's supplying protection for the circuit, for the conductors. Let's take a look at 430.31 because Laurel said to take a look at 430.31. Part 3 specifies overload devices intended to protect motors, motor control apparatus, and motor branch circuit conductors against excessive heating due to motor overloads and failure to start. Okay, Laurel, game on. So what we're saying in 430.31, the general requirements for Part 3 overload devices that are intended to protect motors, motor control apparatus, and motor branch circuit conductors. So, here's my problem, Laurel. When I come down here, it says each motor shall be protected against overload. This is motor. Each motor shall be protected against overload. It doesn't say anything about the conductors. Any motor of 1 horsepower shall be protected against overload. That's not about the conductor. Where the sensing element and setting size of the overload device setting selected in accordance with this is not sufficient to start the motor to carry the shall be permitted to be used to provide trip current overload. So that is about the motor starting. Then overload protection, this just says overload protection, so it's very generic. I would say this one would apply to the above statement where it says circuit and everything because it doesn't specifically say the motor. So this is very generic. I would say that's overload protection of the conductor and the motor starting equipment, etc. And then the secondary circuits for, so the secondary circuits of wound rotor AC motors, including conductors, controllers, resistors, and so forth, shall be permitted to be protected against overload by the motor overload device. So the secondary circuits of wound rotor. So that tells you, in my mind, they're giving you a specific permission that the conductors, controllers, resistors, etc., are permitted to be protected against overload by the motor overload device. That would tell you that all of the other examples do not provide protection of conductors, the controllers, and the resistors because it doesn't specifically call it out. And motor, exactly. You're right. But the motor overload or the overload in AC equipment protects the conductor from overload. Overload protection can be at any point in the circuit. It can, Dawn, as long as it adheres to 240. Remember, in Article 240, I'm going to show you another trick. If I go to 240, and I come down to 240.4, protection of conductors, and I say open link in new tab. Now I've got two instances of NFPA link open. There is protection of conductors, so I can't get away from this. There's nothing in 430 that tells me I don't have to follow 240.4. So now I agree with you, it doesn't matter where, but as long as the overload protection of the motor doesn't exceed the ampacity of the conductor, which was 125% minimum, remember? As long as my overload protection does not exceed 125%, or doesn't exceed the ampacity of the conductor, then I could consider the conductor protected based upon 240.4. That's where my head's at. Because there's nothing in 430 that says I don't have to adhere to 240.4. I could go to the next larger size, meaning the next larger overload protection. But there's nothing in here that in 430 that I could find that I'm thinking in part, and I agree with what Laurel said. Laurel is pointing out the fact that in 430.31, it has a general statement, but my problem is that all of these requirements say motor protection. It doesn't say motor and conductor protection. It just says motor protection. Now, let's go back to the general. Maybe I'm reading something wrong. Part 3 specifies overload devices intended to protect motors, motor control apparatus, and motor branch circuit conductors against excessive heating due to motor overloads. Part 3 specifies overload devices intended to protect. I'm confused. I'm confused. Because to Laurel's point, 430.31 is pretty doggone generic, saying that everything in Part 3 specifies the overload device is intended to protect these components. But in 430.32, it tells you the motor. Each motor used in continuous duty applications. Now, if this would say each motor, if this would say each motor, motor control apparatus, and motor branch circuit conductors that are applied for motors used in continuous duty or that are applied for continuous duty applications, and where the motor is more than 1 horsepower, must be protected by overload, and by one of these means, then I'd be okay. But now, when I'm looking at the values, I see 125%. I don't have a problem with that. Here's where I have a problem. I've got 170. I've got 156. And I've got 140. That's my thermal overload. But that's only when thermal protectors are integral with the motor. But that's about the motor. What about the conductor? I don't have thermal protection in the conductor. I just have it in the motor. So I don't believe you can apply all of the aspects that are in this 430.32 and make the assumption that you're protecting the conductor. Because I'm giving you special provisions for these motors to go to a larger value of overcurrent protective device because I have thermal capabilities and for protection of the motor. I don't have that same thermal input coming from the conductor. So I can't tell you if my conductor is overheating. I can tell you if the motor is overheating. And I would say that the insulation on the conductor is probably the weakest link over the motor. So I don't know that I can say by selecting this that I don't have to protect the conductor at its ampacity. That's just my thought. I'm sticking to it. I'm looking forward to your input. That's all I got time for today because I got to jump on another call. I want to thank you guys for dialing in early. I went live a half hour early, and I have a feeling that this is not. I have a feeling that this is not the end of this discussion on 430 and continuous loads and selection of the conductor and the overcurrent device. We've got a long journey ahead of us. Stay tuned, and we'll see you next week. Take care, stay safe, and please stay healthy. Thanks, Don.